All right, so next up is the Arrhenius equation. And so the Arrhenius equation gives us the relationship between the activation energy and K, the rate constant. And K is directly proportional to how fast the reaction is going. So big K, fast, little k, slow. So let's take a look at the relationship between these things. And not just activation energy, but some other things as we'll see. So the equation goes K, the rate constant, is equal to big A, e to the negative EA over RT. So let's take a look at this one, right? We said this was the rate constant. The bigger this is, the faster the reaction is going. Capital A is what's known as the frequency factor. And so this is a measure of how often molecules hit in the correct orientation. And basically, the more complicated the orientation that is required to react, the lower the A is, right? And so this is talking about that orientation thing that we talked about earlier. So we're just going to go with here, measure of how often a collision occurs in the correct orientation. Cool. E is just the mathematical function. EA is our activation energy. R is our gas constant. And since we're talking about energy, we want to use the 8.314 joules per mole Kelvin. And then T here is our temperature, and always this must be in Kelvin. And so you need to know the relationships between each one of these variables and K. What happens when one of these variables increases or decreases? What effect does that have on K? So let's take a look at all of these. So the frequency factor here, as A increases, what happens to K? Well, look at this equation. As A gets bigger and bigger and bigger, K is going to get bigger and bigger and bigger. Right, so that's the orientation factor, right? So a nice symmetrical molecule would have a high frequency factor, whereas something asymmetrical and some kind of collision that requires a very specific orientation would have a lower frequency factor. Next up, we have to think about the negative EA over RT part. And so the math here and the conceptual can get a little bit complicated. So you can either just memorize these things or you can understand them mathematically. So I'll show you the mathematically here. What we have here is y equals e to the negative x, right? We have k equals e to the negative something. And remember, when anything is raised to the negative something, it's actually just its inverse, right? So e to the negative x is just like e to the x, right? So as x increases, y actually decreases, right? As this number down here gets bigger and bigger and bigger, y gets smaller and smaller and smaller. Think about 1/2 is bigger than 1/4, which is bigger than 1/1,000,000th, right? And so as EA gets bigger and bigger and bigger, K is going to actually get smaller and smaller and smaller. And that makes sense. As the activation energy gets bigger and bigger and bigger, our reaction is going to go slower and slower and slower because that barrier to reaction is now getting bigger and bigger and bigger. And then finally, we have temperature here. So this is as temperature increases, e to the x for the e to the x is actually going to get smaller and smaller and smaller, which makes the e to the negative x actually get bigger and bigger and bigger. So what color did I choose for that? Pink. So as temperature increases, K is going to increase. So you can think of this mathematically as we did here, or you can think of it just logically, right? The more temperature we have, the more energy we have in this reaction, and thus the faster the reaction is going to be. Here's just a picture representing that. So you need to kind of be comfortable with these plots of kinetic energy or temperature, and then the number of molecules occupying this state. Remember, as we increase temperature, when we go from T1 to T2, our plot gets kind of flatter, and then it gets fatter in the higher energy state. And so if this right here is your activation energy, only the stuff to the right with more kinetic energy has enough energy to actually react. So we see when we increase temperature, we increase the amount of that. So there's one form of the Arrhenius equation. You should be able to kind of plug and chug your way through that. There's other forms of the Arrhenius equation that are also important. There's the linear form. And this goes, the natural log of K is equal to negative EA over R 1 over T times 1 over T plus the natural log of A. And so what we did for the previous equation to get to here is basically just take the natural log of both sides, and then you'll kind of get to that equation. If you're curious about the derivation, we can do it at some point. And so this is the linear form. So this is your y equals mx plus b, right? And so we can then, in theory, plot the natural log of k versus our x, which is 1 over t. And our slope will be equal to negative EA over R. So this is one way we can solve for the activation energy, right? So let me just draw this little plot here. 1 over T, right? This right here is the slope. It's going to be equal to negative EA over R. And remember, slope is equal to rise over run, which is equal to the delta ln of K over the change in 1 over temperature, right? 1 over temperature. You'll actually see this 1 over temperature in a lot of chemistry and physics types of properties. We won't go over an example in here, but you can check out 12.13 in your book for an example of how to work through these types of problems. And then very similar to this problem, and actually if you take this equation up here, plot the rise over run type of thing, what you'll end up with is the Arrhenius equation in its 2-point form. And so this one says the natural log of K2 over K1 is equal to EA over R times 1 over T1 minus 1 over T2. So very similar to the classiest Clapeyron equation. There's not much more to it. These are just kind of plug and chug type of problems. So you should be okay with these type of stuff.